Hello, everybody. Um, I'm Pierre Sutra. I'm from Telecom Suite Paris, and I'm going to present to you some work to achieve durability and availability in modern systems. So there are two requirements with data today, which is that it's durable, so it resists power failures in restart, and also that it's highly available, which is that it's there most of the time. So most of the time means that you have many nines after 99. Okay, so here it's one example, but in general, cloud services try to achieve 4.9 after 99, which is like almost there, except a few minutes during a year. So to see those techniques, we will first look at methods to achieve durability using non-volatile memory. So in comparison to the talk this morning, it will be a more high-level presentation because we'll not look at that from the point of view of C, but from the perspective of a high-level language, namely Java. And then we'll move to the world of replication and more precisely geo-replication and how we can replicate data over several sites to make it available despite the failure of one of them. So yes, the first talk is about a technique to have access to non-volatile memory, but in the Java language. And the other one will be a technique called leaderless state machine replication and how we can use it to replicate data over several sites. So today we have durability in languages with the help of the file system as Gail presented this morning. So it's slow in the sense that compared to the CPU, it's way slower. It's 1 millisecond to hundreds of microseconds. It has high bandwidth, and to access it, we use the file system interface. And so because data is stored on disk, it's not in the same format as in memory, okay? So to do the translation, this is the same as when we are doing the translation in the network. We need to do a process that is called marshalling and unmarshalling, that is moving, transforming the representation in memory to be suitable for a disk or to be suitable also, that's the same operation for the network. So on the top left, at the bottom left of the slide, you have some code to do this in Java. So you have an object, you transform it through the help of several stream processing functions, and then you write it to the file, and then you close the file. Okay, and the access is made through a tree structure. Okay, the file system is organized as a tree, which is different from what we have with objects when you're manipulating them in your program. And you have to do the translation back and forth. So there is a new medium that has appeared recently that is called a non-volatile memory. So the interesting thing is that it's durable, so it resists to power loss, well, just like the disk. It has high density, so the smallest DIMM is 128 gigabyte, so it's 4 times bigger than the standard DIMM for DDR4. And also the key property is that it's void addressable, which means that it provides what is called a persistent memory abstraction. And as we have seen this morning, it's highly efficient in the sense that you have read and write access at a speed which is close to the one of DDR. So write is almost identical, and read you have 3-4 folds slower. But that's mostly invisible because you have the cache in between. And also you have high bandwidth with the second version being able to achieve a bandwidth that is very close to the one of DDR. And so accessing this medium, as we have seen this morning, is being made with the help of, at the lowest level, assembly code, because the memory is directly accessible from the CPU. Okay, so the thing is that we have this very nice medium, but we need to propose tools to the programmer to use it. Okay, and this morning we have seen how to use the C language to do that, but there are lots of languages around, and many of them they run on a dedicated runtime, and so they cannot use directly the persistent memory. So in this work, what we are going to look is at the Java language, and Java is used in many contexts. And one of them, which is interesting here from the perspective of durability, is the one of data storage and data processing framework. So at the top of the slide, you have a long list of such storage and processing framework, including many of the software made by the Apache Foundation and others. So for instance, I'm sure you have heard about Hadoop or Spark. And those systems that are written in a high-level language, what they have for the moment is the file system interface, which is the standard approach in which you're marshalling and marshalling data. Or they may use also something that has been recently proposed by Intel together with the PMDK and the framework we have seen this morning for C, which is this PCG, Persistent Collection for Java, PCJ. And if we look at the interface, that is the file system. On the right, you have a plot that compare different performance for a read-write benchmark. And that's the performance of different implementations. So in black, you have the volatile implementation, and then you have three other implementation, which is TempFS. Okay, you have the file system is atop the volatile memory, and then you have nullFS and FS. FS is a file system on top of SDD. Okay, and the nullFS is just a black hole. That is, you do not do anything like storing actual software, actual data. You just throw with data. Okay, and what we can see is that the bigger the data is, the slower the system gets in comparison to the volatile mainline. Okay, so it comes from, and the other thing is that there is not much differences between the null file system, the file system, and the temp file system. It comes from the fact that there is the cost of marshalling. Okay, mainly what you're paying, even if you don't write to the file system, is the dual representation. You are moving the data in memory to the disk, and so you have to do this thing. So that's not very efficient. Okay, and the second thing is that you have this dual representation. So if you open those software at the top, you will see a lot of line of code that are just there to maintain the dual representation between in-memory and on-disk representation, the in-memory and on-disk representations of the data. Okay, and it's not illustrated here, but the interface provided by Intel is not very efficient neither. So how can we provide to Java and other high-level languages a nice access to non-volatile main memory? And this is the question that we look at. And the answer we have proposed to this question is to divide an object into two things. First, a proxy, which is on heap, allocated on heap, just like a regular object. And a second thing, which is the persistent data structure, which is not managed by the runtime, the Java runtime, and it is stored inside the non-volatile memory. Okay, so this is this decoupling idea that I'm going to present you. And at the end of this lecture, we'll do also a little practical to see how to do it in practice and to move a volatile object to the persistent word in Java. So this is the key idea, and we have come up with several things to put in practice this idea. So this includes memory management system for the non-volatile memory, a generator of code to move the data from being volatile to being persistent, and also some libraries. The first one is the library JPFA to do atomic block. And the second one is the Untune library of collections for persistent memory. And also, we have provided some low-level API for experts and a garbage collector when the system reboots to tackle the problem of persistent data that is not being used but was allocated before the system, for instance, crashed. Okay, so if you have any question, do not hesitate to interrupt me, of course. So far, so good? Yes, Guru.
Does it address memory management, like dynamic location?
Yes, that's the first line. That is how we do off-heap management of memory, dynamic allocation, and of course also how we unallocate this memory. Yeah, it's part of the tools we are providing.
So you can dynamically grow your object.
Yes, absolutely. It's something that is done at the lowest level, and what you do is basically access objects that are persistent, much like you would do so with a regular Java volatile program. Okay, so let's look at this programming model of persistent objects. So we have this decoupling principle where we have the proxy object that are inside the volatile RAM, and then we have the persistent word with that is storing the actual data. So the persistent data structure is storing the fields of the object. Okay, so it's accessible, those fields, from the proxy with the help of the getters and the setters. The proxy also holds the methods of the object, so the logic of the object, and it's intermediating the access to the persistent data structure from the point of view of the programmer. The programmer is simply accessing the proxy object. And this proxy is instantiated lazily in the sense that only if we need an object whose content is persisted, we'll actually create the proxy. And those objects are alive when reachable. So that is, we have a set of persistent routes, and if it's accessible from those routes, well, the object is alive. So it's called persistence by reachability. Is a standard approach to define live object in a persistent world, such as a file system or database. So if blocks are not reachable, for instance, they can be collected and reused. So this model is what is called class-centric. That is because we have objects that are proxies, we can discriminate objects that are persistent for non-persistent objects. Okay, so the compiler can help you if you are moving, for instance, an object that is belonging to the persistence word as a reference of a volatile one. You will see it. And the strong typing system of Java is helpful to distinguish what is volatile from non-volatile. Okay, so what is the life cycle of a persistent object in this framework? So we have an allocator, a constructor, which is creating what we need to store the fields inside the persistent memory. And then the proxy is attached to this persistent data structure. So for instance, if we call simple s equal new simple 42, we create a proxy, we create some space in the persistent memory to store the fields of the object. So let's say, for instance, we have a single field, which is an integer, and it's the value that is passed as to the constructor. So it will be stored in NVM as 42. And then we attach the proxy to the persistent data structure in the NVM. The second thing we need is a reconstructor. So the reconstructor is something that is able to reattach the proxy because we want to use one of the objects that are there in the persistent memory. So the constructor is allocating what is needed. The reconstructor is attaching the proxy to something that was created in the past. Okay, and so if needed, we can also construct some soft state, that is some volatile variables that are being used in the computation. And this is done by a method called resurrect. So here, for instance, we are attaching the simple proxy accessible through S to the non-volatile persistent fields that are available in NVMM. Okay, and this data was already accessible through the blue object. And the third thing we need is a destructor. So the destructor is explicit. That is, much like you would remove a file on the file system, you can also free objects using an explicit call to the proxy. So in that case, you detach the proxy, you remove, the persistent data structure, and then you detach the proxy, and the GC, the regular GC of Java, will collect the proxy. Okay, so that's the principle. And now we're going to look at one example to see how we can transform some standard volatile code into persistent code. And what are the underlying principle to do that? Okay, so the goal is to have a layout to put object in the fields of the object into the persistent memory, and also to generate constructor and reconstructor. Okay, so on the left you have the persistent object, on the right you have the transform code. So we have a generator to go from the left to the right, and the goals of the generator are like first defining how we store the object in non-volatile memory, and then we need to generate the constructor, the reconstructor, and also to change a bit the logic of the object such that it is the proxy is able to access the persistent data structure in the same manner as it was doing with the volatile object. Okay, so let's look at the code on the left. So on the left, we have an annotation that says that the object will be persisted, and we'll make everything with this fa equal non-private. Every method that is non-private will be made failure atomic, and we'll have the transformation happen. And then we have three fields in the object. The first thing is a persistent string, okay, this message thing. And then we have two fields. One is transient. This indicates that we don't want to store it in persistent memory. And this one is X, and it's stored in persistent memory. Okay, and then we have the transformation on the right. So on the right, what we have is first, we store the address where the object will live, okay, the persistent data structure. And then we do several transformations. The first transformation is we first remove the field X. I think yeah. Just a sec, sorry. Yeah, okay, sorry. So just for the address. So first we store the address to know where the data will be. And then we define the size of the data structure inside the memory. So the data structure in memory will hold two fields because they are marked as non-volatile. First the message and then X. And there will be a different offset in the data structure. So this is the first goal. We generate the off-heap layout. Then we do two additional things. First, we create the generator. We create the constructor and the reconstructor. So the reconstructor is this code at the bottom. So it takes as input the address and store from the address pass as argument the address of the object it is pointing to, and then is making a resurrection, which is setting the field of the object from the content of the persistent memory. And then we have to wrap the methods as atomic blocks. Okay, I think there is one slide that is, yeah, okay, no, it's there. So we are wrapping the method as atomic block, and we have to change the structure. Okay, because the persistent object we have removed from the proxy all of the field, okay, because they will be stored in memory. So they are instead replaced by setter and getter, and we replace the logic of the method by getter and setters to the field. So, for instance, the increment the x++, the increment of the field x is replaced by a set x of what you retrieve from the persistent memory. And because it's an atomic block, it's written inside this transaction fa start and fa end. Okay, so yeah, all the field access are replaced. That's it. So here, for instance, we are, instead of having this x equal x, we execute the setter zx, and then we set the field that contains the message to this new persistent string hello world. Okay. So this is the set of operation we are doing. We are creating the layout, that is the space in non-volatile memory to store the field of the object. Then we are computing the offset at which each of those sets will be. Then we are removing from the proxy all of the fields that were in the volatile object. We are replacing accesses to the field of the object with accesses with the ones to the persistent field in the persistent memory, and then we are wrapping the methods that need to be with atomic blocks to have atomicity. That's the 4 steps to move the object from the volatile world to the persistent world, and we have a tool to do that automatically. Okay, so now let's look at the accesses to the field, okay, because there are those operations that are doing magically the set and get to the field. So how they are coded in practice below. What we provide to do this is a set of primitives that are accessing and accessing in the sense of reading and writing primitive types in Java. So, for instance, the read object take as entry the address, okay, and the offset at which we store the persistent string, and it returns this object, okay? So it's a low-level operation that simply look at the appropriate position inside the non-volatile memory and fetch the content. Similarly, we can do a write of some value at some location. So, for instance, here it's at the address of the persistent object and the offset 0. And the read and write for int or similar in spirit. Is it okay? This thing. So it's like low-level library. Yes.
As I see in get message, you read only a pointer to the string.
Mm-hmm.
Where is the actual content is stored? The array of chars.
Yes. So the array of char is much like chars or strings instead of in Java. That is, you have a map of all of the strings, and you use this to store all of the strings. Okay, and then based on this map, you that is on non-volatile memory, you store the address of this. So here it's storing the reference, okay? Much like you would do in Java. So the string or like some specific type that is managed by the JNVM. Okay, the framework is managing strings because they are like some of the types that are provided to the user. We provide to the user some collections and included also some persistent strings, so you don't have to do anything. If you would have your own persistent object here instead of a p string, in that case, you would have written it somewhere in the disk, and we store the location on the disk. I mean, like on the non-volatile memory. We store the location of this object in the field, which is this message field here. You see? So we store addresses, basically, plus some magic to like do pointer swizzling because we need to load and store this several times. Yes?
If I want to access the actual Java string, printed somewhere, requires a copy from non-volatile memory to the GVM memory, right?
Yeah, you need to do that. If the string is in volatile memory, you need first to make it a persistent string, a p string.
Does it happen on every read, or does it get cached somewhere?
Okay, I see. I mean, if you're creating strings on the fly, I can't do anything in the sense that you will have to. The transfer.
I just want to read it many times.
If you read many times the p string, okay, it's related to caching of the proxy object. The thing that you move the string from the volatile word to the persistent word, you have to do it. Then it's a p string. So the question is, how can I reconstruct the p string? For instance, if I'm reading several times the p string, and this point is related to how you create proxies. And we create proxies. So we have several collections depending on the usage, but creating proxy on the fly, that is, every time you need them to access some persistent object, we create it, is to some extent already a good performance provider. You already have good performance this way. Yeah, so that's, we don't recreate the thing every time, but we create the proxy when you need it.
And you store the string in the same representation that Java does, this modified DTF encoding, right?
Yeah. Okay, so I'm going to not detail how we. Yes, please.
I wanted to ask, how do you deal with the garbage collection?
Okay.
How do you delete other objects? And what happens if you access inside the constructors or somewhere else. Not this string, but just regular string.
Okay, so for performance reasons, we don't have a GC running on persistent memory. Much like you don't have a GC for the file system or the a database, because it's going to spend its time looking at the objects there, okay, the data there, and saying, oh, it's persistent, I have nothing to do. So we don't do this. What we provide is an explicit free method, okay? And then to deal with problem related to failures, we have also a pass at the start of the program that ensure that you don't have memory leaks. Because when you're doing like this code, you allocate an object, some durable data from the non-volatile memory whose size is good for the size of the class, okay? And this thing, for the moment, is maybe not linked to the program, okay, by transitivity from the roots of the program. So you will have some leak of data if it fails. So we have a first pass at the start of the program to collect this data such that you are not losing memory, okay? But we don't run like online GC for performance reasons.
Also, I have quick question. What if I use simple.x?
Yeah.
Some other code should be replaced with
Yes, it is replaced by getx. You must have all of the access to accessors. I mean, strictly speaking, it's more object-oriented. Like you're constraining the language to be really object-oriented in the sense that it goes through methods every time you need to access a field. It's similar to Java beans, for instance. You constrain also access to those beans in Java through the accessors, and you must do it. So it's the same constraint here. Okay, so we have to ensure atomic blocks redo lock mechanism that is inspired by Romulus and that is working at the level of the blocks that are being allocated and disallocated by the memory management layer. I will not detail that, but in spirit, it's similar to this work. One thing what we do is that we do not log updates to new persistent object. So the idea is that it's much like when you are executing writes to update an object in a database system. As long as the object is not reachable, you don't mind, okay, that you have some pending object, because if things crash, you restart and the object is invalid, so it doesn't matter. So we do the same thing, that is, we do not log the fact that new things are being created, because we have this GC pass that will clear up everything that is non-reachable. Okay, so we have also two things that are provided. First, dropping replacement for some of the collections, and also classes of the JDK. So for instance, string and arrays and maps. And we have also access, we provide access to low-level abstractions. So Gal this morning was presenting PWB, pfence, and psync. We offer them in Java. And also we offer access to the block allocator. And we have this mechanism based on validation that makes atomic reclamation easier, and that permits you to efficiently implement multiple allocation of persistent object. So the idea is that each object has a flag saying that is valid or not. So when we create a new object, a complex object that contain objects that are also persistent and created either within the creation of the complex object or elsewhere, we do not validate the object until the creation of the lowest object is done. And this ensures that objects that are both valid and also reachable are alive, but otherwise they are not alive. So with a single switch, we can define that the object is valid, and if the system fails, they will be discarded. So it's a technique to avoid having p-sync and p-fences, too many of them that will decrease performance. So yeah, here the complex, if once it's reachable from a persistent object, we validate here, but otherwise, if a failure occurs in between, we don't mind. Okay, so this avoids having to push to persistent memory every modification we do. Okay, so we have used this framework in the case of a data store system, which is called InfiniSpan. And in this plot, we compare the performance of InfiniSpan with our modification. Well, we have two flavors of the modification. First, the modification in which we use atomic blocks everywhere in the benchmark, and the other one where we use our custom collections, and that can do smarter things, like for instance deferring the validation of an object. And we compare it in this graph versus the file system approach, and that is like natively what InfiniSpan is providing, and also PCJ. So this is the Java layer on top of the PMDK of Intel. And so we do this with this machine, but we use a single socket, and we have 4 DIMMs of Optane generation 1. And we have the comparison here. So we have different workloads. Some are read AV, others are write AV. I will not dig into the detail, but basically this is way faster with our framework than doing the usual approach. In particular, because you don't have to pay the cost of marshalling. This is the first slide, one of the first slides I was presenting. That is when you are moving the data back and forth disk. Of course, it's you have to transform it every time, so it's very expensive. And an interesting observation we have made also is that we don't need a volatile cache. So in those systems, you have a cache. InfiniSpan historically was named JCache, so it was a cache for object, and that was able to distribute data. And in fact, the cache part is of no need. We can disable the cache, and the system is as fast as with the volatile cache. So to do that, we have hacked the way the persistent layer in InfiniSpan was working, and we have written in around 200 lines of code something that is using instead the JNVM framework. And so it was possible in this very large code base, which is hundreds of thousands lines big, to just do small modification to inject support for non-volatile memory. We have another plot here, which is the performance of 3 versions, 4 of them, in fact. So the volatile version, where there is no data actually stored on disk, the file system, a backend, so the regular one in InfiniSpan, and 2 others which are GPFA without GC and the regular GPFA. So we see here that the time to recover after a failure, so the failure is happening at around 1 minute of the workload. And we see the different speed at which the system is going back to the normal throughput. So here it's TCP TPC-B like benchmark. So it's kind of a banking benchmark where you're moving money from one account to another. And we are in a client-server setting. That is, we have like a REST interface connecting the client and the server. And after 1 minute, we send a SIG kill signal to the server, and we restart it right after that. And this is the performance that the client that is accessing remotely the server is observing. So we can see that the approach is way faster than the file system. Interestingly, in this application, there is no need to do a traversal of the graph of objects to see if there are blocks that are that have been allocated but are not reachable. It's because there is a single atomic operation, so you can disable, if you are an expert programmer and you know what you're doing, you can disable the GC pass at the restart, and you can win a little bit. So on this plot, you win a tiny bit. That's the difference between the orange and the red curve. It's possible, and it will still be correct. Okay, so do you have questions about that, the performance? Okay, so I suggest we have around 30 minutes to give it a try. So it's a practical as this morning. You can do a git clone at the address there. So the slides are available on the shared repo if you want to use the slides as a guidance during the practical. And you can see the instruction in the markdown file. So the practical is made for IntelliJ, because I saw that I knew that there were many people from JetBrains, so it's a IntelliJ-based practical, and it's a practical in which you will do by hand the transformation from the simple volatile object to its non-volatile representation.